So, chi-square tests. Picking up where we left off last time in class, just to recap a little bit, a chi-square test is different from previous things because this actually relates to proportions of outcomes for categorical variables, which is different than what we've done before. So we're not going to have any p-hats or x-bars in this one. You can see we're making some claim about some proportions, but those are not their own variables. This is not successes versus failures. This is how the outcomes for some categorical variable are going to be divvied up. Just like the point of other hypothesis tests or significance tests, where we're trying to claim something about some population proportion or some population's outcomes, we're now using our sample as a basis for this. And we're saying, all right, our sample, honestly, is probably going to be different than the proportion, just due to sampling variability. It would be weird if every pack of M&Ms that we opened up had exactly 13% browns. In some cases, that would be impossible, depending on what N was, how many M&Ms were in the bag. What we're going to test is basically, are our results so far away from what's expected that it's probably not due to sampling variability, that it's more due to any of these being incorrect. And as we talked about in class, when one of those is incorrect, then at least another one has to be as well. Like if the proportion of orange that we find in the bag is 25%, well, the rest of these can't be all exactly the same, lest we end up with 105% of M&Ms in the bag, because that's impossible. So these are our hypotheses. In terms of calculating the chi-square stats, we need to come up with some observed values versus some expected values. So the expected values are actually pretty easy. That would be the case where, I'm sorry, I'm picking through colors here. If the amount that we expect to get is exactly proportional to what's stated in the population. So since we have sample sizes of 100, this is easy. If 16% of my 100 were green, I would get 16 green, 20 for orange, 24. I think I said this before too in class, but like if I had sample sizes of 50 instead of 100, then each of these would be halved. And yes, we would still work with the fractions. Right here, we don't round the expected counts. I would have 6.5 browns for my expected value, 6.5 reds, so on and so forth. What I would suggest is you pause it here and you fill in your observed in your notes. I'm just going to grab 100 M&Ms. I know it's amazing, I haven't eaten them all. And try to fill in the observed portion myself and then fill out the row beneath it. So I'm going to pause the video to fill in everything else. You should probably do the same with yours. All right, there we go. Of course, yours are going to be different depending on what you got in your bags. But those are my observed counts from what I picked up. We want to test now to see if the observed, you can actually see none of the observed are the same as what's expected, but we want to see if it's so different, the O's and the E's, that it actually raises question about our null hypothesis, that these percents actually are what the Mars company claims they're going to be. We do this kind of the way that, and this format here should be very similar to the way we calculated residuals, and even the terminology, like observed and expected. So we'd want to account for a couple things. One is that we do O minus E to see the difference, how far away we are, our observed counts from what we would expect. And then the squared also. There was squared when we were dealing with residuals because we wanted to make sure that being way above or having a way positive difference and then way negative difference wouldn't cancel each other out. So we'd essentially want to look at the absolute value of the differences, but rather than using an absolute value function in order to make it non-negative, we squared it. And then to keep it all relative to the scale of the problem, we divide by the expected value as well. I'm pretty sure this is something that's on the formula sheet, but I'm going to have to double check that. As far as actually calculating this stuff goes, you can do it by hand. Like for this column, I could do 15 minus 13, which is 2, squared is 4, and then 4 divided by 13 comes out to like 0.308-ish. But the good news is, you could have your calculator do all of this automatically. And if you want to try this out, I would really suggest it. Throw your observed in L1, throw your expected in L2, and then in L3, you can actually do, and be careful with like parentheses so that this is good with PEMDAS here, L1 minus L2 squared divided by L2. And the calculator will be smart enough to know that you would match things up, kind of like match pairs, where things in rows would correspond, and then they would subtract, and then so on and so forth. And it'll spit out all of the corresponding entries. So again, I'm going to pause this so that I can fill everything out because you don't need to really watch me do that. I would suggest doing it with yours too. Okay, so here's what I got. Looks like a pain in the cheeks to do by hand, and I guess it kind of is. But there's a good way to automate this. So like I said, if you do the L1, L2, L3 thing, then you get the row in purple on the bottom. But for the sum, for the chi-square stat here, There's a way to do this in your calculator that's not too bad either. If you go to stat and then do one variable stats, one var stats, and then comma L3, it'll give you, I think it's like the second option down, it'll give you the sum of everything in that list, which is exactly what you want here. And it'll look like this. You're in at least pre-calc, so you know that the sigma notation there means sum. When I do that, I get like 4.691. If you're not happy doing your observed counts, you could do mine, it doesn't matter. As long as you know how to do this stuff in your head. Or not in your head, but on your own. So some things to consider here is, what does this actually mean, 4.691? If this were like a z-test or a t-test, that would be a huge test stat. That would indicate that our thing was like 4.5 standard deviations above the mean, which means it's way, way, way unusual. But that's not what this actually represents here. Still, we should think of it in terms of what this number means, what a big chi-squared versus a small chi-squared actually means relative to the difference between expected and observed. So consider the following question here. If the null hypothesis were true, would we expect the chi-square stat to be large or small? Well, if h sub O were true, then we would expect whatever differences we find in the observed and expected to be simply due to sampling variability, which means we'd expect them to be kind of close together. So because of this, we would expect, if O and E are pretty similar to each other, we would expect their difference, what I just circled, to be small. So I'm not going to write it in here because you don't need to see me write it. Check the note key though, because that's still uploaded. But we would expect the chi-square stat to be small. In the answer key, I elaborate on that. But essentially, you could see that I'd have the sum of a bunch of fractions where the numerator is somewhat close to 0. And if the numerator is somewhat close to 0, then I'm adding a bunch of things that are all pretty close to 0. So, in terms of examining this new distribution that we have, the chi-square distribution, a simulation gets me something that looks like this on the left, for starters, and then also just to kind of sum up what we did in the previous page. We would say our chi-square stat is going to be the sum of all cells, where we do observed minus expected squared over expected. That's how we generated the chi-square formula on the previous page. It's how we're going to be generating our test stat moving forward. Degrees of freedom makes a comeback in this distribution as well. Thank goodness it's actually pretty similar to the previous one. It's the number of categories minus 1. When I say number of categories, that really means number of potential outcomes for our categorical variable. So since we had 6 colors, our problem's degree of freedom would be 6 minus 1, which is just 5. Kind of like the t-distribution, the degrees of freedom would change the shape of it, but it still maintains pretty much the same shape, depending on the degrees of freedom. Just kind of elaborate some of the features. Like, in this case, the smaller the degrees of freedom, the more skewed right it actually is. You could see in this example to the right here, where the smaller degrees of freedom of 5 gives a more right-skewed thing, and it's more humpy on the left. Also acknowledge that we can't end up with a negative chi-square stat ever, because observed minus expected squared is always going to be something either 0 or positive, so this thing bottoms out at 0. Which again is another example why our 4 point whatever didn't actually mean 4 points away from 0. 0 is not the mean in the chi-square distribution, it's actually the bare minimum. We would also see as the degrees of freedom increases, just like with a t-distribution too, as the degrees of freedom increases, the shape approaches normality, which is nice. Another thing that's nice is that we're not actually going to do confidence intervals with this, that's not a thing here, just hypothesis testing. So, despite the fact that our null hypothesis involves proportions, we're not actually, like, notice on the previous page, we didn't deal with any p-hats or anything. We worked with the raw counts, the expected counts, and the observed counts. So we're not going to have to worry about proportions. We're just using raw counts to generate our test stat that way. And again, we generate our test stat with this new fancy formula, which I'm certain is on your formula sheet the more I think about it. The conditions, let's just breeze through these quickly, because I know you know these, or you should. These are pretty much always going to be the conditions for inference, because if we don't have any of these, then something's wrong. Either one of the formulas that we're using won't apply, like in the 10% condition, either our data is not indicative of the population, which means any interpretation of it would be bad, or our distribution won't look as we think it would. So in this case, and this is a bit different than what we would expect normally, the expected counts, which were NP, that's how we got them in the table on the previous 2 pages ago, I think, is greater than or equal to 5. If you're wondering why 5 instead of 10, I don't know. It's kind of arbitrary. I guess whoever looked at the distributions decided, like, you know what, if we expect 5, that's close enough. That looks chi-squared-y enough in order for this to work out. So that's fine. I'm sure if you get this confused on the test, like, we've looked at rubrics before where it's like 5 or 10, depending on whatever, I don't know, whatever. Those would both work in the grader's eyes, and that's really all that matters. The cutoff point, as we discussed in class, is kind of arbitrary. So, just looking at the facts here, this is similar to what we've done in previous tests in that we are comparing our p-value, or the probability of calculating our test stat, or something more extreme, to some level of significance, which is alpha, which is usually like 5% or 1% or 10%. If we look at this diagram on the bottom, this chi-squared distribution, whatever my chi-squared stat was, let's pretend I'm actually dealing with mine for a second here. Crap, what was it? Hang on, I'm going to pause it and go back. Okay, 4.691 was mine. If I want to know the probability of getting something like this or something more extreme, that would imply a bigger difference, or a bigger net difference between the observed and expected, which would result in a bigger chi-squared stat, which would make this right-tailed. In fact, for that reason, all chi-squared stats are going to be right-tailed. I'm telling you, chi-squareds are kind of easy compared to the stuff that we've been doing, if we have that knowledge still. Again, this thing bottoms out at 0. And I'm now asking, what's the conclusion of your hypothesis test? The way we would find this is with a fancy function in our calculator called chi-square CDF. So you should take out your calculator. You should find it for easy accessibility. I'm going to pause the video to use it to find my chi-squared stat, and then I have my chi-squared stat. To use it, rather, to find my p-value associated with it, and I suggest you do the same. Okay, I used my calculator, and in it I put, by the way, chi-square CDF, and then lower bound, comma, upper bound, comma, degrees of freedom was 4.691, comma, bunch of 9s, comma, 5. Because remember, our categorical variable was color, of which we had 6. 6 minus 1 is 5. So our degrees of freedom was 5. I did that, and I got a p-value of, like, 45%. 0.45 and change. Boy, that's not that big of a deal. Of course, with our previous knowledge, we should know that that means we fail to reject H sub O. If this were an actual, like, graded thing, you should then put, because this is less than alpha, we fail to reject. And our conclusion here is that we do not have significant evidence that the claimed proportion by the Mars company, the claimed proportions by the Mars company of outcomes, is incorrect. We don't have evidence to disprove that. Not that we have evidence to prove it either, remember. We just don't have good evidence that would say otherwise. So, on the next page is one from start to finish. If you want to do it on your own for practice, that's great. Pause it now and try it. But I'm just going to go through it. Pretty much the way we start these is always the same. I'm trying to make this work with it. The behind the scenes here was not easy to make this happen and reveal it in segments, but we would name the test, or we would use a formula. I'm doing both here just because it's the good teacher thing to do. It's a chi-squared test for goodness of fit. That's what the GOF stands for in the document name. Yes, there's other types that we haven't talked about yet. This one's a goodness of fit one. What we're essentially doing in this case is we are trying to provide convincing evidence, rather, that maybe the quarters of the year have different birthday rates associated with them. I phrased that wrong, but go ahead and read the problem above. We're trying to find if there's convincing evidence that the birthdays of all NHL players are not evenly distributed among the 4 quarters. I really doubt they are. In the population, by the way, they're not evenly distributed. It's not the same per month for reasons. What we would do is pretty much always state the hypotheses. We could do so, unlike the other ones, it's a lot more easily done to state the hypotheses here in words than with symbols. The null hypothesis is that the birthdays of all NHL players are evenly distributed, which is that 25% of people are born in each quarter. The alternate is that this is not the case, or that there are some proportions that are not equal to 0.25. So for conditions, boy, do we know these by now. A random sample, I think this says somewhere that this is a random sample. Yep, this is a random sample of 80 NHL players. We would have to say that 80 is enough, which it is. because in each category, if this were split into quarters, I would expect 20, 20, 20, and that's greater than 5, that's fine. And in terms of independence, yeah, we'll say there's more than 800 NHL players. I think that's true. Let's pretend it is to make this work. And then as far as actually getting our statistic, we have to use the formula. Please don't do any of this by hand. Please jam it all in your calculator. Note that our degrees of freedom is 3 because we have 4 potential outcomes for this. So 4 minus 1 is 3. We get a chi-squared stat of 11.2. When you throw that in your calculator, and also make sure to, hang on a minute, make sure to show this part too. The area of interest under the curve, that's important. I feel like maybe I've been a little loosey-goosey about that. But the stuff we jam in the calculator is lower bound, comma, upper bound, comma, degrees of freedom. We get 1%. So the way to interpret that, because that is indeed lower than alpha, any reasonable alpha, 5% at least, is that we do have convincing evidence at the 5% level of significance anyway, that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Woo! So this video is longer than I thought. I apologize for that. We will continue next class.